progress. Yeah, today, so we're very, very happy to have our second Frontier Condensed Matter Physics seminar series. And today's talk will be given by Igor Zaliznyak for Brookhaven National Laboratory. And Igor and I know each other for a long, long time. He's been an absolute, expert in neutron scattering, does all kinds of wonderful things. I noted his recent paper on sort of this spin chain compound, but in the paramagnetic state. And I was intrigued by it. So I invited him to give this Frontier Condensed Matter Physics seminar class, and so that we can learn more about this particular system. Yeah, so it's all yours, Igor. You can get started.
Okay, thanks a lot, Pencheng, and the organizers for inviting me to give this talk. And thanks to Oak Ridge colleagues for providing this nice venue, because as I mentioned, it wouldn't have been so easy for me to give it from the hotel. So I will present some of our recent results on spin half chain material in the at really high temperatures, and which show that the spin excitations actually retain quantum coherence at temperatures which are much larger than the interaction scale of between the effective spins. So essentially, I've just said what I'm going to present, so you know the answer. But now let me show you a bit more about it. So firstly, let me acknowledge right away the collaborators and contributors to this work. So this specific work was carried out by a collaboration from Brookhaven National Lab, neutron scattering. Lazar Kesh, our postdoc, was the lead figure here with me, and then our VNL theory, Andreas Wesselbaum, Alexei Tsvelik, and Robert Koenig provided a lot of input, especially Andreas, who provided us with top-notch DMRG calculations, which we compared with our measurements. And then, of course, most important collaboration was with Oak Ridge National Lab, with Andrei Podlesnyak, who actually was the discoverer of the material that I'm going to talk about. And so it is by collaboration with Andrei that we have started this project. And of course, then Pajarovsky, who helped with measurements, and Andrei Savich, without whom no data reduction would have happened. And the crystal was made for Andrei by Dr. Vasilichko from Lviv Polytechnic University. And I would like also to mention that this work actually grew from our previous work in collaboration with Megan Arson's group, Lisa Wu and Bill Gannon, where the figures there, where we have first discovered how ytterbiums form one-dimensional chains of spins half. And that was in a F-electron metal. That was a big surprise. And then that surprise followed by a discovery of very same behavior in the perovskite insulator, ytterbium aluminum oxide, which Andrei Podlesnak and Lisa Wu and other collaborators from Oak Ridge Lab did. Okay, so here are the references. The main references on this work is on the top, and then the previous work that's related and led to this is on the bottom. So as I mentioned, this work grew from this orbital exchange fractional quantum number excitations in ytterbium platinum lead, and the follow-up work on the spin confinement and longitudinal mode in magnetic field, and then the discovery of this ytterbium aluminum oxide paper by Andrei Podlesnak led group, and our quantification of exchange couplings in the diluted version of this material. All right, so why physics of spin chains is important? Well, not least because a spin half chain is exactly solved and provides one of the cornerstone theoretical tools for solving problems everywhere, from Kondo effect to string theory, which is so that tool is a Bethe ansatz. But also the spin chains demonstrate a lot of important features like topological states in spin one chain at the boundary. These are in-gap states, which is similar to boundary states of surface states of topological insulators. Then quantum critical matter, the spin half chain demonstrates a larger liquid state with exotic fractionalized excitations. These are the excitations I will be talking about. then when you couple these chains or place them in a staggered field, then spinons demonstrate confinement phenomena, which are similar to that seen in nuclear matter. And finally, our main interest in this work was originated from potential applications of spin chain in quantum information systems, because a spin is basically a description of a quantum qubit. And so a chain of spins is just a chain of qubits, and it can be used for quantum applications in principle. So that's our original motivation in this work. In fact, this work was funded as an attempt to understand how we can couple these turbulent spin chains to external communication systems, and specifically laser systems, so we can communicate with these spins by using laser light. The terbium are specifically well suited for excitation with a laser. Ytterbium-doped insulating crystals are actually laser materials, and this ytterbium-doped yttrium aluminum oxide is one of those, actually. The other aspect of importance of spin chains for developing quantum information applications is that spin chains are one of the first subjects that is being studied or modeled by emerging quantum computers and quantum simulators. So here I show a recent paper from Google Quantum, where they have simulated the spin-half chain at effectively infinite at very large temperature to verify that magnetization dynamics obeys Kardashev-Parisi-Young behavior or universality. Well, why did they study it at very high temperature? The answer is that the controlling temperature or achieving a controlled low temperature in these quantum systems is not an easy and not a solved task. Now, there are a lot of theoretical suggestions of how to use quantum spin chains specifically for transduction of quantum states. So if you have two quantum computers and you want to pass the result of quantum calculation from one to the other, two quantum processors, you need to pass that state through some quantum wire, and spin chains are considered these quantum wires. There is a lot of theory on that. This paper has like 1,500 citations. This one proposal of how to transduce quantum states through a chain of spins. But then there are practical realizations of such proposals, or attempt to practically realize such proposals by building artificial chains of artificial spins, such as quantum dots in silicon or germanium, which have two states, which can be described again. So any two-state system, any doublet system can be mapped on a quantum spin. And so here is a cutout of a recent paper where a chain of 4 quantum spins, effective quantum spins, was used to transduce a quantum state. Now, another way to simulate quantum chains, or to gauge emerging quantum simulators by simulating quantum chains, is by simulating spin behaviors using the one-dimensional chains of atoms in optical lattices, which can be tuned to effectively be described as a chain of spins half with tunable spin interactions, tailored initial state, so you can place your spins in any state you like by using manipulations with lasers. Again, these are effective spins. So this is another attempt to verify Kardashev-Parisi-Young superdiffusion universality. By the way, these attracted much more attention for some reason that's unknown to me than very nice work by neutron scattering by Alan Shea and Alan Tennant that actually did that on using neutron scattering on KCF3. Anyway, the trapped atoms seem to be more sexy. But what I want to attract your attention to is that, this is from a cutout from Adobe Acrobat, and I checked, I searched for temperature in this paper. There are 0 mentions of word temperature. So it's an experimental paper where behavior of a spin chain is investigated, and the word temperature is not even mentioned. Nobody even knows what is temperature. Is there a temperature? And this is actually not a singular thing. Here's another paper where you have using trapped atoms, this team simulates magnon propagation in an effective Ising spin chain. So they are able to tune their Hamiltonian to be Ising Hamiltonian. They are able to tune their initial state to contain one magnon. But then again, the search for temperature in this paper gives 0 finds. So again, what is it that they are studying? As they certainly are not studying the equilibrated state. So it's some sort of non-thermal short-time evolution. In any case, there is no mention of temperature throughout the paper. And so this one is a good one. I learned of this work. So this is a work where are using array of 8 quantum dots. The team has simulated behavior of short spin ladder. And at least here, search finds 2 mentions of temperature. One, this is archived. One is in the reference list, but then the other one is in the supplementary. And supplementary tells us that the temperatures of their device are around 10 millikelvin. That's the lowest temperature they can reach. And then reading the paper, you see that the exchange Hamiltonian that they can tune has coupling of about 100 megahertz, which is like 4 millikelvin. So the temperatures that they're studying their system at are at least twice or more higher. And this is the strongest exchange coupling I found in their paper. There are 25 megahertz, there's weaker coupling. So these studies, and actually I looked up, I learned of this work at the low temperature conference last month. And I actually asked the authors, what is the temperature that you are studying your system at? And they were honest. They told me that the best we can do is like twice J. So these studies in quantum simulators, in quantum computers, are necessarily done at high temperatures or in non-thermalized state. So the bottom line is that there are plenty of theoretical proposals how to use spin chains as a promising platform for quantum information processing. There are some experimental realizations that are being intensely developed and characterized in synthetic spin chains, but the thermalization and finite temperature behaviors of real systems is completely unexplored, and new solid-state platforms are certainly desired. So we are after a solid-state platform, which is based on using ytterbium, the ground state doublet of ytterbium ion as a possible effective spin half, which is the same as a qubit. And so this is I'm not going to talk more about this, but we have in this work we have developed at SNS, as people here know, a setup for for laser pump neutron probe spectroscopy of optical materials such as this setup was specifically designed by us for probing the chains in ytterbium aluminum oxide, so ytterbium chains, where we can excite an ytterbium from its ground multiplet. I will show later what it is, to a excited multiplet by using a laser, which is a telecom laser wavelength, such as used in telecom using ytterbium ions themselves. And then using neutron spectroscopy, explore how the and then using neutron spectroscopy, explore how relaxation of the initial quantum state of a ytterbium chain occurs as a function of time in the time-resolved manner. So this setup has been developed. We have it actually is present at the SNS, and our hope is that it can be used by general users at the SNS in coordination with people who developed it. So main people are shown here. Lazar was leading this, and Barry, Tyler White, Victor Fanelli, Vladislav, so ORNL team. And there is a photograph of this setup at high spec, and our initial data on which we are still working, but technologically, the time-resolved spectroscopy with laser pumping has been implemented, and we have the data. Okay, so this was the motivation, but the main motivation for the work that I'm talking about is, okay, so we are going to shine a laser on our sample. We are going to heat it. Unlike these, cold atom people, we are going to write word temperature, and we have to tell what the temperature was. So we need to understand whether our temperature will what type of decoherence in the quantum state of our system our laser heating will cause. And that is not at the outset of this, we were not very optimistic, because what I know is if I look at what I knew is, my old measurements in spin-1 chain, Haldane chain, which has coherent magnons at low temperatures. This is a nickel trichloride, and you see this is half width at half maximum, which shows the damping of the magnon, and this is its energy. So Haldane gap recovers above ordering temperature, and you see they would cross somewhere at a temperature of about 2.5 J. So there would be no coherent excitations, and then so there is a very rapidly increasing decoherence in spin-1 chain. So magnons lose coherence at temperatures of the order of J. And then Andrei Zholodev put together a very nice overview of many materials with spin gaps, including Haldane chains, leaders, and they all show actually universal. They all show universal increase of damping or decrease of lifetime, which is shown here in the insert. I think this is not very well working. Yeah, okay, right. So the lifetime becomes pretty short at temperatures which are of the order of exchange coupling. As soon as temperatures exceed the spin gap, the damping basically destroys coherence of magnons. Here is another more recent sort of measurement by Guanyon Zhou and Colin Bromholm's group, where they measure this effect in a yttrium barium nickel oxide. This is a model Haldane gap material. This shows the Haldane gap excitation. This is the gap mode. And then at low temperature, it's extremely coherent with the coherence length or free propagation of this magnon in almost 100 lattice units. But as soon as you warm it up to a temperature that's comparable with the spin gap, the coherence length sort of shrinks and coherence more or less disappears. And in fact, the universality of this phenomenon was explained theoretically in a very nice series of 2 papers by Sajdev and Damle, where they basically explain that when 2 magnons collide, they can exchange their magnetic quantum numbers. And so momenta goes through, but magnetic quantum numbers reflect. So what that means is that your quantum state has changed. Magnon which goes right now carries the wrong quantum number. So it's no more the magnon it was before. And that basically introduces collisional damping. So collisional lifetime. So that's a very nice explanation. And these dashed line in this dashed line in this bottom right panel here shows prediction of this theory. So, okay, no coherence at elevated temperature for gapped spin-1 chains or leaders. So this was not very optimistic. In fact, when we started looking at ytterbium aluminum oxide at elevated temperature, one of the questions was, what are you going to see there at the temperature 20 times the exchange coupling? So this is sort of summary of what I've just said. So spin excitations, which are triplet magnets with gap and gapful spin chains, such as antiferromagnetic Haldane chains with spin 1 or spin ladders, due to this universal scattering where they exchange spin quantum numbers, they lose coherence, acquiring finite collisional lifetime or damping at temperatures where they're thermally excited. And they're thermally excited as soon as temperature equals to the gap. And if temperature equals to the bandwidth, then they are very, very excited and there will be no coherence at all. Okay, so that's what happens to spin 1 chains. However, in spin half chains, excitations, in antiferromagnetic spin half chains, excitations are not magnons. If you look, if you consider a cartoon of what magnon is as a spin flip, you will see that if you create a spin flip in an otherwise antiferromagnetic state, that's an illustration on the left, under the action of the spin Hamiltonian, that spin flip will be will fractionalize into two domain walls here. On the other hand, if you would consider a single domain wall, this is situation on the right, then such excited state actually propagate without fractionalization under the action of the Hamiltonian. So Hamiltonian has S plus, Sn plus, Sn plus 1 minus. So this term simply propagates the main wall, while for a magnet, it fractionalizes it. So the good stable excitations from which one can put together the wave vector carrying translational invariant states for spin half antiferromagnetic chain are these domain walls or spinons. Incidentally, I can mention in passing that if you consider a ferromagnetic state, then for ferromagnet, a spin flip is a good excitation from which you can build the translation invariant state, but the domain wall fractionalizes. Okay. Now, the system we are looking at is an ytterbium antiferromagnetic effective spin half chain. And so one way to look at the ground state of this antiferromagnetic chain, the beta ansatz one is to start from a ferromagnetic state and then build up an antiferromagnetic state by either populating it with domain walls, and you would need as many domain walls as you have sites in the chain. So this is how you build the antiferromagnetic states, by populating domain walls one by one. Or you can actually just flip half of the sites, populating half of the sites with magnons. In principle, these magnons can be mapped onto fermions using Jordan-Wigner transformation. I'll show it later. And this one can use either of the two descriptions, either the spinors of beta ansatz or Jordan-Wigner fermions, to describe magnetic excitation in spin half chain. So in the Jordan-Wigner fermion language, what we have here is a half-filled one-dimensional band, and the easiest way to build up possible excitations of this system is to create particle-Hall pairs. So you can take any particle that is under the Fermi level and place it into any place above Fermi level. And because the band is half-filled, the minimum energy that you can attain is given by this dispersion of the lower boundary, which corresponds to the dispersion itself. But then there is a maximum, as I've just mentioned, this is only a property of a half-filled band. So the existence of the lower boundary of this continuum of excitations, particle-Hall in this case, results from the fact that the band is half-filled exactly and has a well-defined Fermi level below which it is half-filled. So you can take particle from here and create small energy for a small change of wave vector along this line. But if you take particle from here, the minimum energy that you can obtain would be the full bandwidth here. Right. So the minimum energy is determined by this lower boundary, which basically just reflects this dispersion of particles themselves. The upper boundary is the property of this dispersion itself, not the property of its filling, because the highest energy of particle-Hall excitation you can ever obtain if you take particle from the very bottom and place it on the very top. So this upper boundary is obtained basically by taking particle from half-wave vector off the bottom and placing it half-wave vector off the top. And so you have this twice the bandwidth times half the wave vector upper boundary. Okay, so this is how the two-particle continuum can be looked at from the Jordan-Wigner perspective. And here is how this two-particle continuum looks in ytterbium aluminum oxide as was measured by Zaliznyak and Lissovu and others. And this is how it compares with the simulation in their paper. Now, this is what I have just explained you, that at zero temperature, when the band is half filled, there exists a very well-defined lower boundary of the continuum. If the temperature is very, very high, the band is filled uniformly. And so there is no constraint that would limit your energy change for any wave vector in this band. And that means that the lower boundary disappears. For any wave vector, you can have as small energy gain as you like if you move your particle a little bit. At low temperature, that was impossible because all states below Fermi level were occupied. But at infinite temperature, there are states everywhere on the dispersion curve, and therefore the lower boundary of continuum disappears. However, the upper boundary stays. So the upper boundary is the property of the existence of a coherent dispersion itself. So if the only thing you can do is move particles along the dispersion, creating particle-Hall pairs in the language of low temperature. So if the only thing you can do is to move particles along the dispersion, so long as dispersion is coherent, you will have a coherent, very sharply defined upper boundary, which corresponds to the maximum energy that particle-Hall can have. Okay, so this is a cartoon of what one would expect if excitations retain coherence at a very, very high temperature. But again, excitations might or might not retain coherence. As we have seen in spin-1 chains, there are collisional mechanisms that limit their lifetime.
So Igor, what determines if a system, would have coherence at high temperature or not?
Well, for spin-1 chain, so whether collisions can lead to a collision in a lifetime, it basically determines by whether during the collision the quantum state is changing. So in other words, whether particles change their nature. So it turns out, so in most cases, collisions do limit lifetime. However, as we will see, it turns out that these spinons in spin-half chain are so elementary particles that they don't have nothing to exchange. So when they collide, the quantum state doesn't change. So this is sort of exception, I would say.
Okay, thank you.
Okay, so right. One thing I just want to point out is that there are two ways to describe excitations. As I mentioned, you can think of excitations as these spinons, which are domain walls, as indicated here, and then they are created in pairs either by flipping a single spin or by pair flip, as is shown here. When two neighboring spins flip, that creates a small domain of antiphase in the middle, and then under the action of the system's Hamiltonian, these domain walls propagate away. And so this is one way to think of excitations in spin half chain. And it's important. I mean, sometimes in these days, people render physical reality to descriptions of physical systems. Spinons are a description. There is another description, Jordan-Wigner fermions. It's also good. Jordan-Wigner fermions are not spinons. They are exact, but they present an exact representation of a spin Hamiltonian, which is shown here in terms of fermions. For the Heisenberg XX or for the XXZ Hamiltonian, this representation has the gas part or non-interacting part, and then there is a strong interacting part, which is proportional to the exchange coupling between SZ component of the spin. So if in the XY model, SZ coupling is absent, and Jordan-Wigner fermions are just free fermions, and their dispersion is actually, their dispersion bandwidth, this guy, is actually simply J, which is exchange coupling. However, in the Heisenberg chain, when an exchange between the SZ components is added, which is equal to the exchange between X and Y components, we obtain a very strongly interacting fermion gas. It's a fermion liquid in 1D. This interaction term is large. And then dispersion from being 1J is renormalized due to this strong interaction, strong repulsion between these fermions, and becomes pi over 2J. So the effect of this interaction in the Jordan-Wigner fermion language for Heisenberg chain is to change dispersion from 1J to 1.5 or pi over half J. All right, and this will be important later. That's why I speak about that. So, okay, so now to the experimental system. So I mentioned we have discovered this spin half chains in the turbine platinum lead by measuring its magnetic excitation spectrum and observing that in one direction, along L direction of the reciprocal lattice, there is a dispersion which looks very reminiscent of a two-spinon continuum of spin half chain, but with a small gap. And that small gap is explained by the fact that the interaction Hamiltonian is not exactly Heisenberg, but has a slightly larger exchange coupling between the SZ components. So it's Ising-like that generates a gap in spin half chain. And the dispersion along the other directions perpendicular to the chain is absent. Actually, it was a surprise because prior to this work, this material was considered to be Shetty-Sutherland two-dimensional system. So we sort of disproved that completely and were puzzled how does it work and why spin half chain physics arises in a system with 4F ytterbium ions. And this is how it arises. Ytterbium is a beautiful system. It's it's 4F analog of copper in 3D. So it has electronic configuration 4F13, which means it's just missing one electron to filling a 4F shell, which can fit 14 electrons. So it has one hole, and it has very, very strong electron hole spin orbit coupling, which splits the, so F shell has L equals 3. Spin orbit coupling wants to add orbital and spin momentum of this hole, spin angular momentum of this hole. So it splits off this total J equals 7/2 multiplet from total J equals 5/2 multiplet where they subtract by a substantial amount of about 1.2 electron volts. So this is this telecom laser wavelength that is used in lasers, and so this transition is the one that's used in lasers and in telecom fibers. Now, then in the crystal field in the sample or in the material determines which orbital of L orbitals is empty, right? Because it's a crystal field where you can lower the energy by emptying specific orbital. And it turns out that in these ytterbium systems, both in ytterbium platinum lead and in ytterbium aluminum oxide, it's LZ equals 3 or M equals 3 orbital, which is empty or singly filled, if you like. So what that means is that the total angular momentum of this ground state doublet, which is split from the doublets based on other orbitals by at least 300 Kelvin, so 27 millivolt was measured. So this doublet is nearly exceptionally made from Jz equal plus 7.5 and minus 7.5 angular momentum states. Now, no matter what these states are, this is a doublet, so we can always describe it as an effective spin. So any doublet, any quantum doublet, you can make quantum combinations of two levels, and they are described as spin. So the Hilbert space of the doublet, so to say, is this Bloch sphere. So this doublet lives on a Bloch sphere. One can assign the up state to Jz equal plus 7.5, down state to Jz equal minus 7.5, and all other states will be a linear combination, quantum combinations of plus 7.5 and minus 7.5. What is important is that because plus 7.5 and minus 7.5 in transition between plus 7.5 and minus 7.5 involves the change of the angular orbital momentum of 7. This transition is forbidden to a very, very high multipole order. So dipole interactions cannot flip this effective spin half. So if your effective spin half is up, the dipole interactions cannot flip it down. And this is probably one of the reasons that these ytterbium systems are so resilient at high temperature to decoherence, because locally the decoherence that would be introduced by randomly fluctuating magnetic fields is absent. Randomly fluctuating magnetic fields cannot, if you have prepared this system in upstate, randomly fluctuating magnetic field cannot move it into downstates. That's distinct from a copper, for example. There you can. Okay. So, but the other consequence of that is that with neutron scattering, we can only measure states, excited states, which do not change the total angular momentum of the system. So the two spinon states can carry change of the total spin of +1, delta Z +1, delta Z -1, or delta Z 0. There are three possibilities. Of these three possibilities, because of this prohibition of spin flipping, we can only measure delta Z equal 0 states. So we can only measure one component of the triplet spinon spectrum, and that component actually corresponds to entangled spinon states. Actually, it's a Bell state. So the only thing that neutron scattering can measure in these ytterbium chains are delta Z equals 0 entangled Bell states. Right now, how it looks in real space. So these LZ equals 3 4F orbitals look like this. They have hexagonal symmetry, and their tiny little overlaps along one of the directions actually lead to what we called orbital exchange. So this is a real orbital exchange interaction when electron spinning on one of the F orbital can actually move to the other orbital. And in order for that move to be advantageous in energy, you need that the direction of spin is opposite. So this is like a gear chain. So this is the origin of the orbital antiferromagnetism in the ytterbium chains. Okay. And then this is basically an illustration of what I have just said, that this is the only type of the only kind of excitations that we can measure where we flip simultaneously two spins, and that creates two spinons, or particle-hole pair of Jordan-Wigner fermions, which is just a different description of the same excited state. All right, so the punchline is that in these ytterbium materials, the orbital momentum dominates magnetic moment. The spin angular momentum is sort of quenched by rigidly tied. It's spin orbit, very strong spin orbit coupling just tells the spin to just point wherever orbital angular momentum points. So the real degree of freedom is just Jz, the total angular momentum J, and the lowest doublet of J is plus minus 7.5 doublet, which can be described as an effective spin. However, that effective spin half, the states of that effective spin half translate into states of the observable magnetic moment in a strange way. One can think of it as a very anisotropic G factor, such that when effective spin points along Z or along minus Z direction, you do see magnetization, but when it points in the X or Y direction, the magnetization is zero, because the combination of plus and minus, quantum combination of JZ plus 7.5 and minus 7.5 states basically cancel each other. The orbital overlaps are the reason for the existence of spin dynamics, and this is important because there are many systems which are purely dipole system, dipole interacting system, but here, and in fact, it was also a surprise because originally there was a conundrum, at least I was told when I started this 10 years ago, that there is no exchange in F systems. Orbitals never overlap, but actually they do. And our results basically prove that. Okay, so we observe a continuum of two spin-on entangled belt states, and what I'm going to tell you next is that it survives to an extremely high temperatures. Oh, by the way, I have a comment on an effective spin half. There is a lot of confusion associated with effective spins. Now, what I want to emphasize, the effective spin half describing our doublet is a real normal quantum spin half. It obeys normal quantum mechanical commutation rules, and all other rules for spin half operator is isotropic and represented by Pauli matrices. It's a normal spin half. It transforms, the only symmetry transforms according to is a two-dimensional representation of the SU2 group. No octupole, no quadrupole, no hexactapoles which were proposed. This is SU2 spin, that's what it is. All these multipoles only come when you transpose these quantum spin states into magnetization density states of your material. So, for example, this is a recent review of different states of dipole octupole pyrochlores based on cerium 3+, which is 4F1 state, and you know you have all sorts of octupolar, dipolar, octupolar, dipolar, and mixed orders. And there is a confusion in the paper. You see that spin component as Z transforms like an octupole or a dipole or whatever. Some effective spin components transform. It's not effective spin component that transforms like that. It's the magnetization density associated with it that transforms like that. And in order to understand that, I'm really a little bit disturbed by this confusion that exists. So the question you might ask, so you see this phase diagram with all these phases. What happens if you have the same structure with the same Hamiltonian, but cerium is replaced with titanium 3D1? What happens to this phase diagram? Lines will change, coloring will change, names of phases will change, nothing will happen. Yes, only names will change. The phase diagram will remain exactly the same. Just names, dipole, quadrupole, whatever. All these tags you will have to rename it in some different way. Because the phase diagram is a property of this effective spin Hamiltonian. And then how these phases reveal themselves in the practical measurement, that's all these dipolar, octupolar, and quadrupolar. That's what they stand for. Anyway, I say that because in our one of the reasons I emphasize this is because the low symmetry of these magnetizations that are associated with different components of the effective spin often is taken for the reason for a spin Hamiltonian to be strongly anisotropic, effective spin Hamiltonian. Now, effective spin Hamiltonian that we have refined in the terbium-2 platinum-2 lead was a bit anisotropic in accordance with the Ising-like coupling of effective spin to magnetic moment. However, miracle, in the terbium aluminum oxide, which has exactly the same Ising-type coupling of effective spin to magnetic moment, right? The G factor is exactly the same. It's maybe even more anisotropic. So you have only G factor non-zero for the Z direction in real space. But the exchange coupling is absolutely isotropic. It was such a surprise. So the effective exchange coupling has nothing to do with the Isingness of magnetic moment, which basically is an expression of your effective spin states in your magnetic state. It was so surprising. It was first refined by Andrei Zaliznyak and Lisa Wu and collaborators, just by comparing the spin spectrum with the calculation. But then we measured the 5% doped yttrium aluminum oxide. If you have weakly doped matrix where most of the ytterbiums are replaced by non-magnetic yttrium, then most of the yttriums are just single ions, but about 7% of the yttriums for this doping of 5% form dimers. And then within a dimer, the exchange coupling is the same as within a chain, and that exchange coupling causes the splitting of single triplet splitting of the state, which is illustrated here. And if there would be a anisotropy in the exchange coupling, then this transition from singlet to triplet would be split into two transitions. So the triplet would be split into two levels. But as is shown here, the peak is single, so the exchange coupling is very isotropic, to better than 10%. It was a big surprise, but so what we have at hand is an ideal Heisenberg chain of effective spins. It is coupled to magnetic probes such that you can only see one of the effective spin components, but that's okay. And that's what we measure. So this is finally the measurement that we have done at different temperatures. So you see the two-spinon continuum at a rather low temperature, 2 Kelvin, that's of the order of J. You still can recognize the lower boundary as well as the upper boundary. Then we go to temperature of 10 K, which is about 5 times J. You still recognize upper boundary very, very well. 40 K, which is about 20 times J. The upper boundary is still very, very well recognized. Only at 100 Kelvin, you do observe some smearing of the upper boundary of the two-spinon continuum. And so on the right, we have the ideal DMRG calculations. And in the middle, we show the DMRG that is corrected for the experimental effect, for the instrumental resolution, and also artificially broadened by assuming some finite Lorentzian width, which emulates the lifetime of a single spinon. And we actually can fit that broadening, and I will show you the result of that fit on the next slide. But and this is basically the same data, just represented in terms of dynamical spin susceptibility. So this is obtained simply by applying a detailed balance to the measured data here on the left, or to calculated data on the right. And then, because at high temperature the chi double prime goes down, we have to scale it by T over J, and that's important. I mean, because it is small, by virtue of having 1 over T multiplier, does not mean you can neglect it. It's like Curie law. Curie law, whatever the temperature, susceptibility can be large, but it still contains Curie constant. So even though susceptibility is very large at very small, at high temperature, Curie constant is uniquely determined by that susceptibility. So very similar situation here. So the chi-double prime has to be multiplied by T over J, but it's very important to for the analysis. So here are the fits of these data from which we can extract the effective broadening that we need to introduce in order to model the smearing. So the smearing only is present clearly at 100 Kelvin. So these are the fits of the chi-double prime. These are the fits of the original data. Now, the top two panels here show the results of these fits. Basically, the top left panel, this one, shows the effective damping of our single spin band. So how well it is defined. And up to 50 Kelvin, which is 25 times J, is below our resolution, so we cannot say nothing. And that corresponds to effective coherence lengths if you take the spin and velocity and multiply by its lifetime. We obtain coherence lengths of about 37 lattice units. That corresponds to our resolution limit. And only above 50 Kelvin, roughly, we see the broadening of the spin or the spin lifetime, and that broadening or damping shows a thermally activated behavior. We can fit it to thermal activation, and we obtain the activation energy of the order of 20 millivolts, which is consistent with the next crystal field level being populated. So what happens is that our description in terms of spin halves accounting for the ground state doublet is no more valid because some of them are actually in the next doublet state. So yeah, so that's nice. So that means that we know what is the limitation on the coherence. It's the excitation of the next state. We also, because this was a quantum information sort of project, we calculated the quantum Fisher information. This is some integral of the spectral weight, which basically some integral property of this spectral weight here of chi-double prime, which imposes a lower limit on the entanglement. Yeah.
So you show the gamma as a lifetime of the spinon?
Yes. No, inverse. So this is 1 over tau.
1 over tau. So could you explain the relation between the spectrum you measured and the gamma?
Okay. Once again, right. So what we did is, we can do this. So we take the calculated by the MRG line shape, and we convolute it with a Gaussian instrument resolution, and then on top of it, we convolute it with the Lorentzian.
Is that P is decoherence of Pearson mode?
Sorry?
Decoherence of Pearson, the lower boundary of the excitations?
No, we only have the upper boundary.
Upper.
Right, but here's the thing. So we don't even rely on the existence of the upper boundary. We take the exact DMRG calculation, right? This guy. And we just fold it numerically with the Lorentzian. If you think of how a two-particle continuum is constructed, it is an integration of a delta function expressing the conservation law between the two-particle state and sum of the two energies of each of the states, right? So two-particle continuum is obtained by integrating the delta function. However, if your states are no more delta functions, they are Lorentzians. Then your two-particle continuum will be obtained by integrating Lorentzian in place of delta function.
So which Q? Or
at every Q, we integrated it with a Lorentzian, but we assumed one single width. So for all Qs, we folded this spectrum, or we integrated the spectrum with a Lorentzian of a given width. Right, just to broaden the upper boundary if it needs broadening, and we fitted that width. So we basically introduced Lorentzian blurring of a spectrum along energy axis. Okay, so we blurred spectrum along energy axis by using Lorentzian. That replaces delta function when lifetime is finite. And this is how our fits look. And then that intrinsic Lorentzian width that we need to blur is shown here. What it says that below 50 Kelvin, we don't need any extrinsic widths. We only need widths that would blur our spectrum. So we compare instrumental measured spectrum with the DMRG. So below 50 Kelvin, that comparison does not require us to broaden the spectrum. But above 50 Kelvin, 60, 80, and 100, we do need some blurring, some Lorentzian blurring, and that this gamma is the width of that Lorentzian that we use to blur the spectrum. And that basically tells us that you had quasi-particles which were sort of delta functions on this dispersion, right? And that corresponds to infinite lifetime. And now when those quasi-particles have finite lifetime, then they are Lorentzian functions on the following the same dispersion, right? And so we have basically determined that Lorentzian width, which corresponds to the lifetime of the quasi-particles sitting on that dispersion, or of spins, or Jordan-Wigner fermions, whichever this description you prefer. Okay, so returning to the quantum Fisher information, there is nothing, it gives us not much insight because at these temperatures, the entanglement depth is less than 1. So it gives lower limit on the entanglement. And so at these temperatures, that limit on the entanglement is less than 1. So, but we still have some interesting, nice scaling of this quantum Fisher number as a function of temperature, like 1 over T squared. I don't know what that would mean and whether it's useful at all, but it is there. Okay, but what is actually useful and interesting, and this is again something that Alan Shea and Alan Tennant did for KCF3, when you have chi double prime, you can Fourier transform it into real space-time. And this now I think that we have to do always with neutron data, because then you can get some information that is difficult to extract from the spectrum. In particular, you see when you Fourier transform, you see the wavefront propagation velocity directly. So you can basically just measure the velocity of your quasi-particles by a ruler. And what I just need to mention is that in the original Alan Shea's paper, they looked at real part of, they Fourier transformed the scattering function that they measured. But the only thing that makes sense, that has physical meaning, is the Fourier transform of chi double prime. Its Fourier transform is the Kubo response function. The real part is just folding of that chi double prime Fourier transform with some cotangent. So its real part is just derived from that. And I think they paid attention to the real part because by virtue of this folding, it's larger in magnitude. So you need to multiply chi double prime of R and T by T. But in any case, chi double prime is a beautiful number quantity, which actually allows you to directly obtain the propagation velocity. And that's what we did. This is still unpublished, but this is actually quite beautiful. So this is all our same data that I have shown. Actually, it's more data here from 2 Kelvin to 80 Kelvin. And you might actually, if you look carefully, you will see that the upper envelope of 2 spinon continuum actually goes down in energy. Mm-hmm. And if you look at the Fourier transform here, you would see that opening of this V actually becomes sharper at higher energy. What that means, that excitations become slower. And if we refine velocity of these excitations from these measurements, we obtain this curve here. And what this curve tells us, it's very nice to think about it in terms of interacting Jordan-Wigner fermions. At low temperature, the interaction renormalizes our free fermion velocity by factor 1.5. But as temperature increases, that effect of interaction becomes weaker and weaker and eventually goes away. Electrons become asymptotically free of interaction. So at infinite temperature, Jordan-Wigner fermions become free, even though they are strongly interacting. Well, Sorry, I probably was a little bit long, but I think it's, oh, not bad, 1 hour. So basically what I've shown here is that spin excitations in the ytterbium aluminum oxide transparent perovskite, which actually is a suitable system for developing quantum information platform interfacing quantum spins with lasers and photonic devices, the spin excitation coherence is preserved up to very high temperatures. We have determined the limit on terminal coherence by comparing our measurements with the MRG calculations. And this isn't published, but I think it's a very remarkable results that at high temperatures, one-dimensional interacting fermions become asymptotically free. And finally, this all shows that ytterbium systems in solid state actually have great potential for quantum information technologies. Thank you.
Yeah, thank you, Igor. Yeah, very interesting talk. I mean, let me ask you sort of let me ask you first, and then if other questions arises, I'll ask you. So why is it this particular system is so different from other sort of spin chain compound where you said in your introduction that the damping immediately sort of cues any sort of a potential quantum coherence. Why is this so particular?
So there are several, several aspects to the answer to that question. So firstly, this is spin half chain. So the spin half chain, which is integrable and has especially the Heisenberg one, which has these excitations which are gapless and are so elementary that they have no mechanism of collisional damping. So the chain itself is not destroying its coherence of its excitation by just thermally populating the excitations, unlike spin one chain. But secondly, if I compare now the rare earth effective spin half chain based on ytterbium, or maybe other like cerium, I think it's the same. So this ground state doublet is protected from local decoherence. So if you have just a single ytterbium or a single cerium, it can, if it's copper, then locally, as I mentioned, locally fluctuating some random field can actually flip the spin from up to down. But this is not the case for these rare earths.
I see. So you would not expect it in spin of a half chain?
Sorry?
You would not expect this if you have a copper spin of a half chain, which does not have this doublet.
Well, this is an interesting question. This is a very interesting question. So copper spins do have this mechanism of decoherence, which is absent here. In other words, if there are some impurities or something that are a source of fluctuating magnetic fields, these would be a source of decoherence for copper spins, but not for ytterbium effective spins. But this is a problem that should be experimentally investigated.
Okay. Yeah, very, very interesting. Yeah, and any other questions for Igor?
At the beginning, you mentioned that this decoherence is universal between spin chains, spin ladders.
Right.
Would
so
the
it's
same thing apply to this ytterbium? If you would have a ytterbium spin half ladder, that you would be
yes. If it would be a ladder such that the elementary excitations become rich in quantum numbers, right? So you have a triplet magnum. It has +1, -1, and 0. Then you create this should be Sajdev mechanism, or not but Sajdev-Damle mechanism for collisional lifetime effects. So my sort of hand-waving view of this, spin half highly coherent spinons is that they are so poor in quantum numbers that there is also some sort of a whatever conservation laws they have in their collisions, doesn't change that.
So why is it the bound state? I mean, it's so well defined, even at such a high temperature in your case.
Well, it's not a bound state. It's a boundary.
Yeah, sure. Why is that so well defined?
Well, okay, that's actually a very good question. In fact, we were sort of helped by this basically property of Heisenberg's spin half chain, that most of its excitation spectral weight at all temperature, just it's a property of the of matrix elements, or what of this. It's a property of the chain of this specific, that even though 4 spin-on, 6 spin-on, multi-spin-on states are allowed, and they would have higher energy. However, the calculations show, and our measurement agree with that the spectral weight contribution of those states to spectral weight
so
is
much
like
smaller.
1%. Is very, very small. So in that sense, we were aided by this fact, because if those contributions would become large, it would be very difficult or impossible for us to state the coherence, because you would have spilling of spectral weight into multi-spin-on excitations, but there is no such spillage according to theory and according to our measurement.
Okay. That makes sense. Yeah. Okay. And any other question for Igor?
Yeah, I have one. So you showed basically this is persisting up to the excitation to the first, excited state. So in terms of other thermodynamic things like susceptibility and specific heat, does it look like a highly frustrated system, or is this just because you essentially have a very clean background, because you just said you don't see these other multi-spin-on things? This is the scattering you see, but the relative amount of this is actually, smaller, right?
So firstly, speaking of frustration, there is no frustration. It's just 1D unfrustrated chain.
Yeah.
So it just...
Sorry, does it look like a transition to an ordered state or not?
Oh, okay. So speaking of transition to an ordered state, and that's something I should have said, but I have not. So you see, this measurement is done at 1 Kelvin, and do I not have it? I think I do. Yes. So sorry. So this measurement is done at 1 Kelvin, and this is base temperature. So there is a transition to the ordered state. Ideal spin half chain never orders. However, when you put them in a coupled array, they sort of cooperate with each other to order. That ordering is very weak, occurs usually at a temperature, or can occur at a temperature which is much lower than characteristic coupling scale. So in the case of terbium aluminum oxide, the ordering of the magnetic order does occur at 0.8 Kelvin. So in the ordered state, instead of this continuum immediately collapses, because there is the mean field acting there is a mean field of a neighboring chain acting on the chain, and that mean field causes this confinement phenomenon. So spins confine to form a magnum. So this is a magnum, and this is the remainder of the continuum. That all occurs at a temperature that is determined by interchain coupling, and it's much smaller than, substantially smaller than the in-chain coupling.
Yeah, that makes sense. Yeah. Okay, it's already 3:10. Yeah. Thank you, Igor, so much for this very nice talk. Yeah, very illustrative.